accelerator to trigger a nuclear reactor. Yes.
Right,
So
because
what
you want are basically an external source of neutrons.
Okay, we're going to begin.
Okay.
Good morning, everybody, and for those who are overseas, good evening. I'm glad to invite all of you here for this gathering because we have a very eminent speaker. More about the speaker will be given out by Dr. Mayank Bahia. I just thought I would explain why NMIMS University and Free Press Journal got together. We got together because as a publishing house, which prints newspapers, has a website, we are also in the business of information and education, just like a university, like NMIMS University is. So in some ways, both of us had tremendous synergies. And we said, why don't we come together and promote ideas for the audience to talk about things that the country also needs to understand and know. And that is how we decided to have the series on power. And we had the overview with Praveer Sinha. We had the solar power by Ashish. And now we have the third one. And next week we have wind power. But before we go ahead, let me tell you what the audience thinks. And for that, if you remember, when we had just a minute. And then if you remember, when we started this series, when we asked you to register, we asked you a few questions. We wanted to get a feel of what you thought. So if you look at the nuclear poll results, we'll go back to the first poll that we conducted, where everyone thought solar power would grow the fastest, but 10% thought that nuclear would grow the fastest. Why, I do not know, and it's up to a chief speaker and Mayank to find out how fast will the sector grow. When we had specific questions on the session, everyone believes that India will go in for more nuclear power at a very rapid rate. Only few people believe there could not be very rapid a growth. And when it came to safety, almost 3/4 said that safety is a major concern in the nuclear sector. And this is something that I thought my co-panelists would like to be aware of, and the audience would also like to know. With this, I begin. I stop the screen share, and we go back to the talk. To go back to the talk, first I'd like to ask Dr. Mayank Bahia to introduce our chief speaker, who is someone who's been reading for the last so many years. Dr. Mayank Bahia.
Yeah. So it's my pleasure to talk to you about this issue of nuclear power and India's power requirement at a time when there's a projection that India will need 3 times as much power as it needs today over the next 20 years. Every possible source is an issue and every source has to be understood. So today, to understand the issues related to nuclear power, we have a very eminent person with us who has in fact written books on the power of promise, examining the nuclear energy in India, and has worked on various issues related to nuclear power in India for the last several decades. So Dr. Ramana is with us, and we are very grateful that he's with us. He's a very distinguished Simons Chair at the Department of Global and Human Society at the School of Public Policy and Global Affairs. And he has done extensive research, like I said, on international security, energy supply, including nuclear weapons and their impact, including pollutions from coal and how to control those issues and all that. And he has also, therefore, been a member of various journals, various issues related to fissile material, on international panel on fissile material, on energy research, and so on. So he's somebody who knows not only the nuclear scenario of the world, but he's also very aware and very well learned about the nuclear scenario of India and the issues related to that, as well as the future that nuclear energy holds for India. So I will not stand between you and Dr. Ramana. It's my pleasure and a privilege to invite Dr. Ramana to please talk to us about the nuclear scenario in Indian context in the future. Thank you very much.
Thank you very much. Thank you very much, Mayank and Bhaskar, and thank you so much for inviting me. Thank you all for listening. I'll sort of share a little bit about what I know on this issue. To start with, I'm going to talk a little bit globally first, and then I will talk a little bit about India. And I want to start by actually referencing the poll results that Bhaskar showed, which is an interesting thing. So if you look at nuclear energy, it's probably, without any debate, the most controversial source of power. There are people who feel very strongly that it's a bad source or it's a good source, right? And it's very difficult to find people who are completely neutral about it. And broadly speaking, there are two kinds of narratives that often go with nuclear power. So one narrative focuses on some of the problems with nuclear energy, right? So in this poll, you had sort of asked about safety, and many people had talked about it. And the nuclear power is unique in that it's the only source of power where if there is an accident, the contamination can spread out widely across space and time, right? So in the case of the Chernobyl accident, for example, radioactive contaminants from it were found in every country in the Northern Hemisphere, essentially, right? And that contamination, primarily cesium-137, still contaminates large areas in Belarus, in Ukraine, in parts of Russia, and so on. Several thousand square kilometers are still uninhabitable. Okay, so that's something which is unique about nuclear energy, and we saw similar sorts of things in the case of Fukushima in Japan, right? The second concern that many people who are worried about nuclear power talk about is the fact that, again, it's one of its unique properties is that the generation of energy automatically comes with the generation of radioactive waste materials. And these are hazardous to human health. If you go near that, you can get a fatal radiation dose, your chances of cancer go up, and so on and so forth. And these materials, substances stay radioactive for hundreds of thousands of years. So if you want to produce nuclear energy, you will have to deal with these waste products and keep them away from coming close to humans for this unprecedented amount of time. Just to put that in context, you cannot put up a sign saying radioactive waste buried here, because there is no guarantee that somebody who's living 100,000 years down the line is going to be able to read English or Marathi or Hindi, right? We can't read what is written in the Harappan script now, which is just a few thousand years away, right? So that's a second very unique aspect. And the third, and depending on whether you're a supporter or an opponent, the linkage between nuclear energy and nuclear weapons is something which is essentially not separable, right? Any nuclear reactor automatically produces plutonium, which can be used to make nuclear weapons, right? So for those people who don't like nuclear power, that's a negative point. And for those people who like nuclear power, that's actually a great political selling point, right? Because then you can go to countries and say, look, I can also make this bomb for you guys, and therefore you should support us, you should give us. Okay, so that's one set of ways to think about nuclear energy. Another narrative about nuclear energy, and this is the older narrative, if you like, about nuclear energy, starts by positing that nuclear energy is the way that we can power our civilization, right? And that is actually the words that Homi Bhabha used in 1955 when he spoke to the UN first conference on the peaceful use of atomic energy. Similarly, when Nehru was setting up the Atomic Energy Commission, he was talking about the fact that it is because India did not have steam power that India got colonized, and therefore now we need to get into atomic energy. Otherwise, we are going to be forever underdeveloped and colonized, and so on and so forth. That he doesn't say that, but that's the hidden implication, right? So this idea that you need atomic energy to provide electricity, right? This used to be the primary argument. And over the years, that argument obviously has lost some, the evidence is against it, primarily because we don't have a lot of nuclear energy, and yet we do have electricity, right? So it is not a necessary way by which you can generate electricity, right? But the new argument that has come up is that in order for us to generate electricity without carbon dioxide emissions to combat climate change, we need nuclear energy, all right? And so that's the other argument that you see quite often. And again, there's a debate over that, can you do it with renewables and with batteries and so on? And I don't want to get into that. We can get into that in the question and answer session if you like. So there are these broad two narratives. But there's a third way to look at the whole thing, and that's what I'm going to focus my sort of discussion on, which is to look at the numbers, as it were, right? So how much nuclear energy are we talking about? So if you look globally, there are about 440, if I remember right, is the last count I remember seeing, nuclear plants around the world, officially according to the International Atomic Energy Agency. These are spread out around 31 countries, okay? And if you look at the kind of distribution, what you will see is that there are a handful of countries, 5, 6, 7, which have a fairly large number of nuclear power plants. So India, for example, has about 22 nuclear power plants officially. The United States has about 95, that's the maximum. France just shut down 2, so it's now down to 56. So there is a bunch of these kind of countries. And then there's a large tail, if you like, where many countries have built 1 or 2 nuclear plants and then stopped, essentially. Okay. Together, so these nuclear plants were primarily built over the 1970s and 1980s. There were 2 big waves of construction. The first wave was in the United States primarily, and then the 1980s was primarily in Western Europe. And then since the 1986 Chernobyl accident, the rate of construction has fallen tremendously. And what you see since then is that the number of plants that are being constructed is roughly equal to the number of plants that are being shut down on many years, right? So there are some years when there are more plants constructed and some years when there are more plants that are shut down, right? So that's how the overall number of plants has more or less remained flat for the last 20, 25 years. But what's interesting is if you think about how much of the global electricity nuclear power supplies, what you see is that the maximum share of electricity around the world has been 17.5%. This was in the year 1996. And since then, it has been declining almost monotonically, as it were. And it's come down to about 10% today, right? And even under the most optimistic forecasts from the International Atomic Energy Agency and other agencies like that, nuclear power will at best maintain market share, right? And most likely will actually decline further. This is not because nobody's building plants, but because everybody's building many more of other things, right? And so if you ask the question, why is this share declining? The simple answer is that nuclear plants are very expensive to construct, okay? I will come back to this point later, but I'll just stop it there at this point. I just want to now turn to the numbers in India, if you like. And so if the global fraction is about 10%, in India, the fraction of electricity generated by nuclear power has pretty much consistently stayed between around 2 and 4% for about 20, 25 years at this point. In the old days, they used to talk about the Hindu rate of economic growth at being around 3%. And this is sort of like that. It's been around 3%, goes up a little bit every time there's a new nuclear plant built. And then once, other sources of power are built up, it'll come back down, right? So it's been sort of oscillating between 2 and 4% for a long time. So in the last set of numbers that have come out, nuclear power contributed about 3.2% of India's electricity. Now, just to put that in comparison, both solar and wind energy have contributed more than that in the last few years. Solar just overtook nuclear energy last year in terms of how much electricity it contributed to the grid. Wind has overtaken it sometime around 2012 or 2014, if I remember right. Okay, so both of these, of course, are much more recent. Nuclear energy has been around since the 1940s. 1948 was when the Atomic Energy Commission was set up. And it sort of these much more later technologies have taken off in a way that nuclear energy has not done. And this is something which you saw in your poll results as well. Most people think solar energy is going to expand a lot, and nuclear energy, much fewer people think it's going to expand, right? Now, so coming back to this question, why is nuclear energy in this sort of share? Why is it not sort of increasing dramatically, right? The first thing I'd say is that this is not, I'll give you a reason why it is, what's a wrong reason. It is not because governments have not supported it. There's been a historically, every government has essentially supported nuclear energy, would like to expand India's nuclear energy production, right? So it's not for lack of political support that it has not grown. Instead, there are, I think, 4 or 5 important factors which I think really sort of guide. So the first thing is that if you look at it historically, there has been a long-standing idea that nuclear energy is going to expand rapidly, and the Department of Atomic Energy has come out repeatedly with projections. So in the old days, in the 1960s, they would talk about, the first projection was for about 8,000 megawatts by the end of by 1980, and then that went up to about 25,000 and the highest actually was 43,000 megawatts by the year 2000, which was put out in 1970. Okay, and the actual numbers have never met those projections. So if you look at the projection for 2000, the actual number was about 2,000 megawatts. So roughly about 5% of what was projected, right? That number, then of course, people have come down a little bit. So the projection for many years by the end of the 1990s was by 2020, we will have 20,000 megawatts, right? So it's a nice, rhyming sort of number. But if you look at what is the current capacity, it's about 6.8 gigawatts, 6,800 megawatts. Right, so it's not as bad as the 5% that used to be there, but it has not really grown very much, right? And you look in the future, they have sort of come up with similar projections for the future, which undoubtedly they will miss. What that you can take as a prediction, right? Given the history, right? But there's more to this than just the history. The fact is that nuclear power technology is a very complicated, complex technology, right? One way to think of it is that a nuclear plant is essentially a way to boil water, right? To produce steam. That's what a nuclear plant does. But it does so in the most complicated way possible, right? Dealing with extremely hazardous substances and so on. So naturally, you have to build a very complicated machine, right? And when you build complicated machines, things go wrong, right? And this is why you have accidents, but this is also why it costs a lot of money to build, it takes a long time to build, and so on and so forth, right? So there is this inherent nature of the technology. And if you look at how India has sort of proceeded, in each of the projects that they have done, you will find that there are new problems they're coming up with. So if you look at the reactors that are being built in Kakrapar, they're delayed. If you look at the fast breeder reactor that's being built near Kalpakam, that is being delayed. And for reasons which I can go into during the question and answers, right? So there is a series of problems that you come across, and it's not as though the space of problems can be exhausted, right? Because this is fairly unique technology, which is built in very few places, you are going to be coming up with newer and newer ways of finding problems with this. So it's number 2. The other issue which has come up in since the 1980s has been that everywhere India has tried to build a nuclear plant or tried to mine for uranium, etc., there has been public opposition, right? And this opposition has been, for the most part, unsuccessful in trying to stop. There have been a few exceptions in Kerala, in West Bengal, and so on. But for the most part, what has happened is that when there is opposition, the Indian government has essentially dealt with them by sending in the police. So that's what happened in Kudankulam, for example. And the movement there was just beaten back. But regardless of what you think about that whole process, the more important thing for the story which I'm telling you is that when there is opposition, there can be some delays. For example, they can go to court, they can try to challenge the environmental impact assessment clearance, etc., etc. So those are ways by which the lack of public support is going to slow down a technology, right? And then there is one other very unique thing about India, which is that for historical reasons, which have to do with Homi Bhabha and what he envisioned for the future of nuclear energy in India, the Department of Atomic Energy has focused on a particular kind of nuclear technology called fast breeder reactors. This is the one that's being built near Kalpakkam. And fast breeder reactors are, if nuclear power plants are complicated, fast breeder reactors are doubly complicated, all right? So there are huge sets of problems with fast breeder reactors, which make them very operationally very difficult to deal with. Right, and I can, I don't want to get into the sort of the nitty-gritty technical details about why breeder reactors are difficult, but the fact is that in most parts of the world, everybody started by thinking, oh, we need to build fast breeder reactors, and primarily because everybody was expecting nuclear power to take off a lot, and they were expecting that the world would run out of uranium. Now, it turns out that A, nuclear power did not take off the way initial scientists and engineers expected, and B, the world has a lot more uranium than they knew at that point, right? So we are in no danger of running out of uranium. So breeder reactors also turned out to be much more difficult to build and more expensive and so on and so forth. So most countries, Germany, the United States, the UK, all of them had fast breeder reactor programs. They've essentially given up on them, right? For historical and sociological reasons, India has sort of said, oh no, this is a very important part of our atomic energy program, and pours in a lot of resources into that. So even if you're going to be supporting nuclear energy, this is not the technology that you should be focusing on, right? That's what I would say. And finally, I will say one last thing, which is that if you were to think about nuclear energy as a way to help development, to provide power to the hundreds of villages which may not have power, or so on and so forth, nuclear energy is a very bad choice in a way. Why? Because what you need for development is cheap energy. And instead, you have probably the most expensive form of energy. So if you look at numbers in the United States and many other places, you will find that a new nuclear plant costs of the order of $20–30 billion, right? I mean, sorry, $10–15 billion. So a twin unit costs about $20–30 billion. And the kind of power it produces is of the order of about $100 per megawatt hour. Whereas solar and wind today are selling at around $30 to $35 per megawatt hour. So it's about 3 times as much. And even if you add in batteries and so on, these days you're finding in these auctions, the combined source of power coming in around $40, $45 per megawatt hour. So nuclear energy is simply not economical. And so for a developing country to kind of say, we need this power and we need to use this expensive source of power is a kind of does not logically work, right? In the early years, a famous economist in MIT said, look, if a man is hungry, he can pay whatever money he wants for a meal, but it'll be silly for him to go and buy a restaurant because he's hungry, right? It's a little bit like that. So you're trying to, you might say, look, electricity is so badly required that we need to use any possible source, but you would not select the most expensive source of power. Right? So that I'll sort of stop there and then maybe cover a lot of other things which I wanted to say in the Q&A.
Okay, thank you. Thank you, Ramana, for a wonderful overview of the nuclear sector. Okay, I will just ask one question, then I'll leave it to Mayank to ask questions, then I'll take over from him and ask the questions that the audience wants me to ask. Okay. There's only one question I have, and that is, you said nuclear power is the most expensive. But governments in India, and I mean governments, I mean subsequent governments, all governments have tried to tell us that it's the cheapest power. Point one.
Yes. Yeah.
Point two, in the same question is, nowhere in the world do they take the cost of decommissioning a nuclear plant as the cost of power. Can you dwell on the factor?
Sure. So the first one is a claim, okay? And you examine the claim, right? And this has to do, I think, partly with the history of nuclear energy, right? People in the early years knew that nuclear energy was going to be expensive, right? But they had to make a case for building it. And so this was a claim that they made. So it was started with somebody called Lewis Strauss, who was the head of the Atomic Energy Commission in the United States. And he was speaking to a bunch of journalists, science journalists in New York. And he basically said, nuclear power will be too cheap to meter at the time of our children and grandchildren, all right? We'll produce electricity that's too cheap to meter. And kind of that story has stuck to nuclear power, right? Now, if you look at any country, and I've done this for India, we have done this for, Saudi Arabia, we talked about a while ago, in the United States, there's every year these companies in Wall Street and so on put out these numbers, all right? So there's no question anymore of that, okay? The second part of it, how does this change when you add the cost of decommissioning waste and so on and so forth? That's a very interesting question. So one way to answer that question is that we actually don't know how much it's going to cost to decommission or deal with the radioactive waste, because there is no operating facility anywhere in the world that can actually store this spent fuel for the hundreds of thousands of years. People have talked about so-called geological repositories. Not a single one has been constructed so far. So we don't know how much it's going to cost, all right? That said, I will turn the thing around. So if you look at how economists do costing, all right, there is a standard procedure. And this procedure it's actually sort of standard in all, capital markets. You do something called discount cash flow analysis, all right?
Okay.
So anything that's a cost in the future is discounted to the present, right? If you do discounting with anything that is being spent 60 years, 100 years, 1,000 years in the future, and you discount it with a non-zero discount rate, it'll essentially become zero, right? It'll be insignificant, right? And basically the argument is, okay, I don't care. Let it say it's going to cost $1 billion. If I put $100 aside every year and I let it grow at some rate of interest, it will reach that $1 billion. That's the argument that they would make. Okay, what actually happens is that, this was the early argument, and most of those plants, when they were talking about, there was no waste to deal with. Now, in the UK, for example, all the old nuclear plants have been shut down, and suddenly what happens is the old utility that said, oh, we've been saving money to deal with this, suddenly say, oh, we only have 500 million pounds, and actual cost of it is 3 billion pounds, right? So the rest of it, where is it coming from? It's going to come from the taxpayer, okay? And in a way, this is actually the way nuclear power has survived in those markets which have been opened up to competition, right? The way it survives, the way companies actually go ahead and build nuclear plants, given all that I'm saying, nobody should be wanting to build it, right? The fact is no. As long as you can find a way to get somebody else to pay for it, it's fine, right? So you privatize the profits, you socialize the costs, you socialize the risks, all right? And that's what you'll see in every place when it's actually being built.
Yeah. Mayank, your area. Your voice. You're mute. I can't hear you.
Yeah, so sorry. So that was a very fascinating summary of nuclear power, its promise, and the fact that it has not stood up to the promise simply because the technologies have become so complex that their original vision of simply taking a uranium atom, splitting it, collecting the heat, they thought would be much simpler than what it turned out to be. So the basic problem has not been with the idea, because 1 kilogram of uranium will produce a lot more energy than 1 kilogram of coal or anything. But the fact that the supporting technologies turned out to be more complex is the reason why we have come to a balance which is now no longer favorable. But the question is that India had one major hope, which was thorium. Would you like to comment on thorium-based reactors?
Sure.
And why it has not materialized?
Sure. So, I will start by saying that in the electronics industry, right, semiconductor industry, there is a joke. The most chips that you use in computers, as you know, are made of silicon, right? There is another material called germanium. And for a long time, material scientists would say, germanium is the material of the future, right? And it never became the material that was being used. And by the 1990s, the electronics industry, they used to joke, they said germanium is a material of the future, always has been, always will be. Okay. Thorium is very much like that. All right. And there are sort of two sets of reasons why that is true. So technically, the reason why thorium is not becoming, used around the world, and many people around the world had this similar kinds of ideas. The French, for example, had the same idea, right? The reason why it does not come to pass is because uranium is still very much available, right? So we are not having a problem because of lack of uranium, right? So thorium is a much more complicated material to use for the simple reason that thorium is not fissile. What that means is that it does not fission in the way uranium does when hit by a low energy neutron, okay? And so what you have to do with thorium is that you have to convert it into a material called uranium-233. And that happens by putting the thorium inside another nuclear plant, which doesn't have any thorium necessarily, and having the thorium absorb neutrons, right? So in the case of the old Bhabha plant, the idea was that you would build a bunch of breeder reactors using plutonium and uranium, and then you will cover that with this blanket of thorium. And all the neutrons that are escaping the core will be caught by the thorium. The thorium will get converted into uranium-233, and you will take that into a reprocessing plant, take out the U-233, and so on, okay? Now, there are two problems with that. So obviously, you can see it's already become much more complicated, right? But the more important issue is that uranium-233 does not come by itself. It comes along with a contaminant, which is uranium-232. Okay? Another isotope of uranium. These are all not things which you'll find in nature because they are unstable. They will be decaying away, right? So whereas U-238, all uranium is unstable, but U-238 has a half-life of 4 billion years. So what was produced during the Big Bang is still there, okay? But in the other things have all decayed away. Now these other U-232, which is coming along with U-233, is a hard gamma emitter. So it produces very energetic radiation. So if you have to make fuel, for example, with that, you will have to do so in concrete facilities where people will not have access to the things. So you have to use remote manufacturing, stuff like that. It can be done, but you're increasing the cost of fuel fabrication heavily, right? So, and there's no reason to expect that thorium reactors are going to be any cheaper compared to uranium reactors. And so all told, there is no operating thorium-based plant anywhere in the world. But if one is going to be constructed, I can guarantee you that it will be more expensive, right? And nuclear power already has the economics problem, right? It does not have a uranium problem, right? So in a sense, thorium is the wrong solution. It is like the person who has a hammer who's just saying, oh, I have a hammer, therefore everything looks like a nail, I'm going to bang it.
Yeah. The second question I had was that one of the problems with nuclear reactors is the fact that you are generating neutrons from inside, and then you have to control them. You have to make sure that the numbers are correct and reaction doesn't go out of control and stuff like that, which is what costs a large part of the resources, as it were. Now, there is another set of suggestion, which is that you can control the neutron generation using accelerators, which will then give you controlled amount of neutrons, and therefore the entire secondary cost of the system would go down significantly, and therefore you would have a cheaper nuclear reactor than what current nuclear reactors are. So remove the uranium as a primary source of neutrons, replace it with accelerator neutrons, and you can control everything, including the flux of neutrons, including the nature of reaction, including the amount of contaminants that you produce, and a lot of secondaries that come out with a nuclear reactor, which makes eventual shutdowns difficult, would be much more simpler. What do you think of that technology?
So I've heard of this a lot. I'm yet to see one of these, and most of my research has been based on studying what's being built. Okay, on paper, everything looks like a great idea. All right, but as somebody said, the best reactors around the world are ones that are built of paper and moderated by ink. Okay, and so on paper this looks like a great idea, but I can sort of try to work with this, right? So the first thing is, you're right that in principle you can reduce some of the safety costs in principle, okay? But you are in turn adding a cost from an external source of neutrons, all right? And to generate those neutrons, you have to generate some electricity from somewhere, etc., etc. All right. So there is going to be a certain set of costs associated with that. The second is, again, on paper, something might look very simple and safe. The question is whether what happens when you lose control over the neutrons, etc., etc. When you take this idea to a nuclear regulator, and he or she is a good safety regulator, they're going to ask a whole bunch of questions that may not be apparent to us, right? So I'm speculating here that if Carlo Rubbia or somebody who sort of came up with this idea were to actually say, okay, fine, I'm going to spend $10 million and hire 20 people to actually develop this and say, here's my design, all right? And then they are to go and take it to a regulator. That is not going to have worked out. That's my guess, okay? Now, finally, I'll say one more thing about going back to this idea of paper reactors and how it is difficult. So in principle, it's very easy to come up with ideas of lots of reactor designs, which all seem simpler, okay? And if you hire a bunch of graduate students and you give them thesis funding for 5 years, they can come up with a group of reactors. But between that point and making a design that is actually ready to be constructed and can be operated safely, typically the investment cost in the United States is about $1 billion. Okay, so you can generate an idea for, let's say, less than $1 million, and then you spend $1 billion to actually move it between that, and because you have to run a whole bunch of tests, etc., etc. Most people will look at these paper designs and say, I don't think I'm going to spend that, forget the billion, even the $100 million first stage, nobody's going to be spending that. So that's where it is at.
Yeah, given the nature of the, why is it even sustained at 10% level?
Yeah, that's a great question. So I think some of this is a factor of inertia, if you like, right? So there were these great promises made for nuclear power, and as a result, many countries went ahead and set up nuclear atomic energy departments and so on and so forth. And then once you set up these kinds of institutions, they have a certain amount of momentum that they have, right? So their job is to go around and saying that atomic energy is the answer for our things. And they will come up with these kind of claims that, it's very cheap. We have these new designs where all these problems are going to be solved. We're going to be producing more fuel than you put in these breeder reactors, et cetera, right? And so, you get a few of these things going in every given country. You have a certain number of construction projects that are happening. And the places where, so I mentioned early on that if you look at the distribution of reactors around the world, there are a few countries where there are large numbers, and the vast majority where there's just a couple of them, and so on and so forth. So in those places, these atomic energy departments and those bureaucracies have not reached critical mass, as it were, to pun on that word. Whereas in these large countries, they've reached this critical mass, in which case they can keep getting funding, right? So regardless of the fact that India has only producing 3%, you will find the Department of Atomic Energy will not be starved of funds, right? Same thing is true with China, for example, right? And it takes a huge amount of political fighting somebody has to be doing to stop that project, right? So it can happen in some cases. So in Germany, for example, partly as a result of Chernobyl, partly as a result of Fukushima, the public rose against it and they said, we don't want to build anymore, right? We want to shut down all of that. And Germany is going through this phase out, which has actually been relatively successful. I mean, like everything, there are going to be problems. They should have done this, they should have done it that way. But by and large, if you look at the trajectory of Germany's coal use, their emissions, their nuclear energy, all of them has been coming down, right? Basically, renewables have more than made up for the loss of nuclear capacity and coal capacity, right? But it took a particular set of social forces to come together to stop this, right? But in other countries, that has not happened, right? Why is there a whole bunch of things you can ask this question? Why are a lot of things which seemingly economically irrational things are being done? And the reasons have to do with social and political reasons.
Before I give it to Bhaskar, just one last question. What do you think fusion as an energy source?
Okay. So fusion, my own sense is that it's a little bit like the kind of question about thorium or about or about these accelerator driven reactors. So in the case of fusion, my understanding is that there are three sets of barriers or three challenges, right? So the first challenge is what one might call a physics challenge, which is how do I create this fusion reaction, which is, as you know, very hard to create because it requires extremely high temperatures so that you go into the plasma phase and you have to hold the plasma together for a sufficient period of time for the fusion reactions to start, right? So that requires these high magnetic fields or these laser driven stuff, etc., etc. So there is an initial amount of energy that is required to even set up the fusion reaction. And then the fusion reaction immediately sort of dies out within a matter of, microseconds, right? So the first challenge is to be able to generate more energy out of those fusion reactions than what you put in to hold the plasma together, right? And so that's, if that is not happening, then you're loss-making proposition.
Yes.
Right? The next challenge is, you want to convert this into an engineering challenge, which is I not only have to generate the more energy than I put in, but I have to do so on a consistent basis. Every second I have to be producing that. If you look at
yeah. So at present, we don't have the technologies to do a fusion reactor. I agree with you on that. But do you think it holds a promise for the future, or is it simply one of those wild guesses?
So I think the story is similar. My colleague, when I was back in Princeton, retired as the director of the Princeton Plasma Physics Laboratory. And he said, when I started working in plasma physics as a young graduate student in the 1970s, we used to say commercial fusion was 30 years away. Now I've retired, I say it's 40 years away. Okay. So
we're not getting hold of the technologies that we want.
I don't think, as somebody who teaches in a school of public policy, I'll say as a matter of public policy, I think it is irrelevant, right? As a scientific challenge, it's an interesting challenge, right? So, there's some reason to be saying, let's keep doing research on it, but I don't think you should hold your breath waiting for it to happen.
Okay, and just one more point. Sorry, Dr. Bhaskar. You have talked about this modular nuclear reactors for some countries and such like that. What is that idea?
Yeah, so so small modular reactors is the latest set of reactor designs that nuclear industry has been promoting as the answer to all the problems that has been experienced with old nuclear power, right? I don't want to get into sort of each of those designs and whether they work or not, but there is one basic feature they all have, which is that they're meant to be small, right? And small has some very good features to it, right? If you have an accident, for example, the amount of material that you can eject is much smaller, obviously, right? And so on and so forth. But there is a reason all nuclear plants, the first nuclear plants were pretty small. They became larger and larger for a reason. And that reason is called economies of scale, right? If you want to build a nuclear plant that is generating 1,000 megawatts instead of 100 megawatts, you don't need 10 times as much steel or 10 times as much concrete or 10 times as many workers, but you can produce 10 times as much electricity. Therefore, it is more profitable to build a larger reactor, right? So when you go back to small, you're losing out on those economies of scale. So you start off being more expensive to start with, right? So whatever else might be the attraction of small reactors, they're going to be more uneconomical by and large. Okay, so I don't think so. There's going to be some which might be built around the world, but I am not at all confident that they are going to solve all these problems.
Bhaskar sir, we have another 15 minutes. Shall we take up the questions from the general?
Yes, we will. Just for the audience, I didn't tell you this, but Dr. Mayank Vahia is the Dean of Mathematics in Narasimhanji University and MIMS University. And earlier he worked with TIFR. So his exposure to nuclear sciences is phenomenal. Unlike me, I'm just an outsider. I'm just trying to understand the subject from both of them. Okay, I just thought I'd give a little explanation about Dr. Mayank Vahia. Many of the people have asked questions about fusion, which fortunately Dr. Vahia has already asked and Ramana has already replied. There are two interesting questions that come up. One is a question by a BARC scientist, Dr. Karkera, who says, why don't we build it under the ocean? Why don't we use dry docks? Hence the export potential and let's say 1,000 square kilometers per station. Coming from BRC, I thought it would be something that you would like to take up.
Mhm. So, I think trying to build it in locations which are, far away from. So why would you want to build it under the ocean, right? The only reason why you would want to build it in part is because you are afraid of accidents, right? So if you keep it, let's say, near Mumbai or near Delhi, and if there's an accident, then you will have to evacuate that city, and that's a problem. We've seen that in Fukushima, we've seen that in Chernobyl, right? So the argument goes, some people have similarly proposed building it underground, right? You build it fairly deep underground, and if there is an accident, well, everything is contained inside there, right? It turns out that, again, the main decider in most of these cases is economics, right? So, if it's already expensive to build a reactor on the surface, building it underground typically will be more. And people have done these calculations, and you can try to say, look, you can save some on the safety by building it underground. But I think most utilities have decided that's not going to be worth their while, okay? With the ocean, there's a special problem. And the special problem is the ocean does not belong to any one particular country, right? So there are laws that govern what you can do, right? So one of the things we cannot do is dump a bunch of, toxic waste into the ocean, right? You can do fishing, but you cannot, throw out all your, unless it's considered to be sufficiently low concentration effluents, right? So the same thing holds true for nuclear waste as well. And now, if you're going to build a nuclear plant under the ocean and there's a possibility there's going to be an accident, who's going to be responsible for that? How are you going to contain it? And lastly, I'll say the idea that you can build in these complicated technologies in these very challenging environments should actually give you a pause. Remember the kinds of accidents you've seen from BP, Deepwater Horizon, or an Exxon Valdez and things like that, which are, challenging areas to be, deep under the ocean is not a good place to be hanging around, right? So I don't see that as necessarily a good solution to the kind of problems we have.
Okay. There's another question about safety. And it says there are two ways of looking at safety. The record of people getting contaminated because of nuclear reactors is much lower than the number of people who die because of other causes. Mm-hmm. That is a question that you should take up. And the second one related to that is you have a lot of depleted radioactive stuff which are lying around. For example, the depleted uranium that was used during warfare in Iraq has repercussions even today. Or the Fukushima disaster, which is having repercussions even today around 3 Mile Island, is another classic case where even today people are scared of the contamination around there. Yours.
Sure. So let me sort of start by going to the question about, how many people have been contaminated and so on. This is a very highly debated area.
Okay.
So for example, in the case of Chernobyl, for a long time, the official Soviet number was that 31 people had died from the accident. All right.
Okay.
And on the other end of it, the spectrum, there was a report that was produced by Yablokov, who was a very respected Soviet and subsequently Russian scientist, and a group. What he basically did was collate all the epidemiological studies carried out in the area that was contaminated, to look at increases in the numbers of thyroid cancers and leukemias and all kinds of things. And they came up with a number of the order of 960,000, right? Close to 1 million. Okay. So that's a huge range, right? And part of the problem is that there is no marker for radiation-induced cancer. Cancer is the most widely studied impact of radiation. Right? There are a whole bunch of other things. We know that radiation can increase chances of a heart attack or all kinds of other endpoints. But the most well-studied thing is cancer. All right.
Or deformed babies.
Deformed babies. So yeah, that's another story. I won't get into that. But yes, definitely there is some reason to worry about that.
Yes.
But back to the question of this, there is no marker for this. What that means is that somebody gets cancer. You cannot say this person got cancer because he or she was exposed to radiation. right? Because a large number of people anyway get cancers in society, right? Anyway, there are deformed babies being born, right? How do you know this is only because of this? And all you can say is, well, look, the rates in these areas seem to be much higher compared to the other areas.
Absolutely.
So this must be because of this and so on. And that is a debated area, all right? So that's one point to say. The second is, if you're saying, what is it you're comparing with? So one way to compare, and this way most people say, is look, radiation is not so dangerous. Many more people die of traffic accidents, car accidents, right? Or something of that sort. There, the issue becomes, how do you compare these two? When I drive a car, I have some sense of control over that, right? I can say, look, as long as I'm wearing my seatbelt, as long as I'm driving on the right side of the road, as long as I'm not speeding, as long as I'm not intoxicated when I'm driving, my chance of accident are relatively low. That's my experience. I see it every day, right? And so I have some confidence that when I go out to drive today, I'm not going to die, right? I could be wrong, because many people do die, right? Or get injured badly and so on. But the fact is, for most people, their lived experience is that this is not a very high risk technology, right? On the other hand, nuclear technology, you have no control over that.
Yes.
Somebody else is operating the reactor, all right? So this is not a good analogy. Finally, I'll just point one more thing. There's another source that you can compare this with, and that's coal, all right? And I think it's perfectly correct to say coal has a pollution impact due to the smoke, due to all kinds of other things, particulates and so on. And a large number of people die, right? Again, estimated to be in the hundreds of thousands, et cetera, right? Now, what do you say about that? And the answer is very simple answer, which I usually say is that, yes, I agree. Both of them are bad, all right? It is like asking me whether I want to die of heart attack or cancer. I don't want either of them, right? For a long time, that was not an acceptable answer because there was no other possible alternative. Today, with the growth of solar and wind and other things, this is now a new possibility. Right? And they have their problems. I'm not denying that, but I'm just saying, for people can look at this and say, well, that argument doesn't hold anymore, right? I don't want either of them, but there are other possibilities. And I only care about electricity. I don't care whether you produce it with a nuclear plant or a coal plant. And if you can produce it with less risk to me, I would rather choose that alternative. Okay. You had a second question, which I sort of ignored, which is, what was that about?
Depleted.
Depleted uranium, absolutely. So this contamination stays, and it is not something which is going to go away, right? Ideally, so if you were to mine any uranium, okay, there are only 3 possible endpoints for what happens to that uranium, all right? On a good day, the uranium becomes radioactive waste that is stored inside a nuclear reactor, hopefully will get buried inside a repository someday in the future. That's the best possible scenario. The second bad scenario is that uranium is going to end up as radioactive fallout from an accident like Fukushima or Chernobyl, right? That's the second scenario, and that's the bad scenario. Then there's a really bad scenario, which is that the uranium atom ends up being part of a nuclear weapon, like being converted into plutonium, and that weapon is dropped over some city and hundreds of thousands of people die, right? That's the worst possible scenario. But there is no good scenario in a way when you mine uranium. They're all bad scenarios.
Okay. One more question before I ask Mayank to propose the vote of thanks. And that question is, with climate change, with weather becoming more inclement and more unpredictable, and earthquakes and tsunamis becoming more common, is there a risk to all nuclear reactors, especially those which are near the coasts?
Absolutely. So the answer is simple answer is yes. So the issue is that, I told you that nuclear plants are complicated things can go wrong, and there's a lot of reason to expect that nuclear reactors are inherently prone to accidents, right? Now, you try to control that by putting in all kinds of safety mechanisms and so on. The thing which happens when there are external events like earthquakes, like storms and so on, is that they can simultaneously cut out different safety features at the same time, right? So for example, in the case of Fukushima, the tsunami simultaneously cut out all external source of electricity. A nuclear plant, strange to say, actually needs electricity coming into the plant for it to be operating safely, to be making sure there's no meltdown, all right? And in the case of Japan, not even for the tsunami, just the earthquake prior to the tsunami brought down all the electric lines that come into the plant. Right, so the nuclear plant in Fukushima Daiichi had to resort to just using the diesel generators it had on site, and those diesel generators got flooded by the tsunami. All right, and so the second level of safety also died out. All right, and so this kind of thing is something which you can expect in many places. Right, so there is always going to be this risk, and there's a reason why nuclear plants are kept near oceans, near big rivers and so on, because they need a huge amount of cooling water, right? And so I think with climate change, that is going to be more of an issue. And what you see, forget accidents. In Western Europe, for example, because those nuclear plants that are constructed in France, for example, were constructed in the 1960s and 70s, thinking about a certain temperature regime. Now what's happening is that in the hot summer months, in France, for example, the water in the river is already too hot. So for it to come into the nuclear plant, cool the plant and go out, it's less efficient, and the temperature becomes even so high that the fish can't survive. So they say, okay, you have to shut down the nuclear plant, all right? So increasingly in the last decade and a half, you find every now and then a few plants having to be shut down in the peak of the summer because they are unable to get cooling water, right? And so this is not going to be, this is going to be more and more of a problem as climate change becomes worse.
Thank you very much. But I'm not going to, the vote of thanks goes to Mayank. Your voice, mute.
Sorry, Dr. Ramana, it's a pleasure hearing you. A rather distressing scenario for nuclear future, but then there are issues of national prestige, like you said, and there are issues of other issues of defense, etc., which seem to keep this industry going for some time. And it looks like it is not going to die out very soon. It will remain at a background level of production. And probably countries and political parties feel happy showing that we are still producing this material. Plus the international security environment is becoming what it is now, it is unlikely that this technology is not going to be developed further. And our best hope probably is to come out with designs which are less technology intensive, and that somehow we can manage this thing going, because per gram uranium still produces more electricity than everything else, but the safety and security seem to outweigh the profit that we have. So we still have a promising source of energy, but the technology surrounding of the extraction of that energy is where the problem is. And there seems to be no end to that set of surrounding problems that we have. So it was illuminating to hear from you directly about what these issues are, what are the problems. It was a very illuminating talk, very pleasant talk. I want to thank you very much. We have all understood the issues much better than we did an hour ago. So we remain grateful to you for that, for illuminating these important issues and technologies that are related to that. And with those words, on behalf of NMIMS, on behalf of Free Press Journal, and on behalf of Tata Power, thank you once again for taking this late evening off for us and illuminating us on this important topic. Thank you very much.
Thank you. One of the most lucid talks I've ever heard. Thank you.
Thank you so much. I really appreciate it. This was a great opportunity, and thank you all for arranging this possibility of, for I can sit in my bedroom and talk to all of you. And share my thing. And thank you again.
Thank you. And next week we have wind power. Do log in.
Yes, great.
Thank you. Thank you once again. Good luck.